Question number 21. What are the various steps involved in an analytics project? The following are the various steps involved in an analytics project. Number 1. Understand the business problem. Number 2. Explore the data and become familiar with it. Number 3. Prepare the data for modeling by detecting outliers, treating missing values, transforming variables, etc. After data preparation, start running the model, analyze the result, and tweak the approach. This is an iterative step until the best possible outcome is achieved. Number 5. Validate the model using a new dataset. Number 6. Start implementing the model and track the result to analyze the performance of model over the period of time. Question number 22. During analysis, how do you treat missing values? Answer. The extent of the missing value is identified after identifying the variables with missing values. If any patterns are identified, the analyst has to concentrate on them as it could lead to interesting and meaningful business insights. If there are no patterns identified, then the missing values can be substituted with mean or median values. Imputation, that is called imputation, or they can simply be ignored. Assigning a default value, which can be mean, minimum, or maximum value, getting into the data is important. If it is a categorical variable, the default value is assigned. The missing value is assigned a default value if you have a distribution of data coming for normal. Normal distribution give the mean value. If 80% of the values for a variable are missing, then you can answer that you would be dropping the variable instead of treating the missing values. Question number 23. How will you define the number of clusters in a clustering algorithm? Though the clustering algorithm is not specified, this question is mostly in reference to k-means clustering, where k defines the number of clusters. The objective of clustering is to group similar entities in a way that the entities within a group are similar to each other, but the groups are different from each other. For example, the following image shows three different groups. Within sum of squares is generally used to explain the homogeneity within a cluster. If you plot WSS as the sum of square distance between each member of the cluster and its centroid for a range of number of clusters, you will get the plot shown below. The graph is generally known as elbow curve. Red circled a point in the above graph, number of clusters is equal to 3, is the point after which you don't see any decrement in WSS. This point is known as the bending point and taken as k in k-means. Elbow curve. This is the graph. This is the widely used approach, but few scientists also use hierarchical clustering first to create dendrograms and identify the distinct groups from there. The algorithm starts by finding the 2 points that are closest to each other on the basis of Euclidean distance. If we look back at graph 1, we can see that points 2 and 3 are closest to each other, while points 7 and 8 are closest to each other. Therefore, a cluster will be formed within these 2 points first. In the graph 2, you can see that the dendrograms have been created joining points 2 with 3 and 8 with 7. The vertical heights of dendrograms shows the Euclidean distances between the points. From graph 2, it can be seen that Euclidean distance between points 8 and 7 is greater than the distance between point 2 and 3. The next step is to join the cluster formed by joining 2 points to the next nearest cluster or point, which in turns result in another cluster. If you look at graph 1 and point 4 is closest to cluster of point 2 and 3, it turns result in another cluster. If you look at graph 1, point 4 is closest to cluster of point 2 and 3. Therefore, in graph 2, dendrogram is generally generated by joining point 4 with dendrogram of point 2 and 3. This process continues until all the points are joined together to form one big cluster. Once one big cluster is formed, the longest vertical distance without any horizontal line passing through it is selected and a horizontal line is drawn through it. The number of vertical lines this newly created horizontal line passes is equal to number of clusters. Take a look at the following plot. We can see that the largest vertical distance without any horizontal line passing through it is represented by blue line. So we draw a new horizontal red line that passes through the blue line. Since it crosses the blue line at 2 points, therefore the number of clusters will be 2. Basically, the horizontal line is threshold, which defines the minimum distance required to be a separate cluster. If we draw a line further down, the threshold required to be a new cluster will be decreased and more clusters will be formed, as seen in the image below. In the above plot, the horizontal line passes through 4 vertical lines, resulting in 4 clusters. Cluster of points 6, 7, 8 and 10. Cluster of points 3, 3, 2, 4 and points 9 and 5 will be treated as single points cluster. Question number 24. What is ensemble learning? In statistics and machine learning, ensemble methods use multiple learning algorithms to obtain better predictive performance than could be obtained from any of the constituent learning algorithms alone. Ensembles are a divide and conquer approach used to improve performance. The main principle behind ensemble method is that a group of weak learners can come together to form a strong learner. Each classifier individually is a weak learner, while all the classifiers taken together are a strong learner. Suppose we have to classify X, classifier 1, classifier 2, classifier 3, classifier 4, classifier 5. So class 1 90% in classifier 1, class 2 is 8%, class 3 is 2%. In classifier 2, class 1 is 10%, class 2 is 80, class 3 is 10, classifier 3 1%, 85%, 14%, 4, 25, 65, 10%, and classifier 5, 5%, 90%, 5%. So average is class 1 is equal to 26.2%, class 2 is 65.6%, class 3 is 8.2%. So highest percentage is class 2, so final prediction would be class 2. Question number 25. Describe in brief any type of ensemble learning. Ensemble learning has many types, but 2 more popular ensemble learning techniques are mentioned below. Bagging. Bagging tries to implement similar learners on small sample populations and then takes a mean of all the predictions. In generalized bagging, you can use different learners on different populations. As you expect, this helps us to reduce the variance error. Pros of bagging. Bagging method helps when we face variance or overfitting in the model. It provides an environment to deal with variance by using n learners of same size on same algorithm. During the sampling of train data, there are many observations which overlap, so the combinations of these learners help in overcoming the high variance. Bagging uses bootstrap sampling method. Bootstrapping in any test or metric that uses a random sampling with replacement and falls under the broader class of resampling methods. Cons of using bagging method. Bagging is not helpful in case of bias or underfitting in the data. Bagging ignores the value with the highest and the lowest result, which may have a wide difference and provides an average result. Boosting is an iterative technique which adjusts the weight of an observation based on the last classification. If an observation was classified incorrectly, it tries to increase the weight of this observation and vice versa. Boosting in general decreases the bias error and builds strong predictive models. However, they may overfit on the training data. Pros of boosting. Boosting technique takes care of the weightage of higher accuracy sample and lower accuracy sample and then gives the combined result. Net error is evaluated in each learning steps. It works good with interactions. Boosting techniques helps when we are dealing with bias or underfitting in the dataset. Multiple boosting techniques are available. For example, ADA boost, LP boost, XG boost, gradient boost, Brown boost. Cause of boosting is boosting technique often ignores overfitting or variance issues in dataset. It increases the complexity of the classification. Time and computation can be a bit expensive. So in this figure we can see on left side bagging, that is parallel, and then on right side boosting, sequential. There are multiple areas where bagging and boosting technique is used to boost the accuracy. Banking, loan defaulter prediction, fraud transaction, credit risks, Kaggle competitions, fraud detection, recommender system for Netflix, malware, wildlife conservation, and so on. What is random forest? How does it work? Question number 26. Random forest is a versatile machine learning method capable of performing regression, classification, dimensionality reduction, treat missing values, outlier values. It is a type of ensemble learning method where a group of weak models combine to form a powerful model. The random forest starts with a standard machine learning technique called a decision tree, which in ensemble terms correspond to our weak learner. In a decision tree, an input is entered at the top, and as it traverses down the tree, the data gets bucketed into smaller and smaller sets. Random forest simplified. So there is instance and there is a random forest tree 1, then class 1, then tree 2, class B, up to tree N, class B, majority voting, then final class. In random forest, we grow multiple trees as opposed to a single tree to classify a new object based on attributes. Each tree gives a classification. The forest chooses the classification having the most votes over all the trees in the forest, and in the case of regression, it takes the average of outputs by different trees. Question number 27. How do you work towards a random forest? The underlying principle of this technique is that several weak learners combine to provide a keen learner. Here is how such a system is trained for some number of trees T. Number 1. Sample n cases at random with replacement to create a subset of the data. The subset should be about 66% of the total set. Number 2. At each node A, for some number m predictor variables are selected at random from all the predictor variables. B. The predictor variable that provides the best split according to some objective function is used to do a binary split on that node. C. At the next node, choose another m variables at random from all predictor variables and do the same. Depending upon the value of m, there are 3 slightly different systems. Random splitter selection m is equal to 1. Random splitter selection m is equal to 1. Breeman's Bagger m is equal to total number of predictor variables p. Random forest m number of predictor variables. M is smaller than number of predictor variable. So there are all data in this diagram. We see that all data, random subset tree, and random subset tree, random subset tree, random subset tree. Then at each node, choose some small subset of variable at random. Find a variable and a value for that variable which optimizes the split. When a new input is entered into the system, it is a run down all the trees. The result may either be an average or weighted average of all the terminal nodes that are reached, or in the case of categorical variable, a voting majority. Note that with a large number of predictor p is greater than 0, the eligible predictor set M will be quite different from node to node. The greater the inter-tree correlation, the greater the random forest error rate. So one pressure on the model is to have the trees as uncorrelated as possible. As M goes down, both inter-tree correlation and the strength of individual trees go down. So some optimal value of M must be discovered. Strength. Random forest runtimes are quite fast, and they are able to deal with unbalanced and missing data. Weaknesses. Random forest used for regression cannot predict beyond the range in the training data, and they may overfit data sets that are particularly noisy. Of course, the best test of any algorithm is how well it works upon your own data set. Question number 28. What cross-validation technique would you use on a time series data set? Answer is, instead of using k-fold cross-validation, you should be aware of the fact that a time series is not randomly distributed data. It is inherently ordered by chronological order. In case of a time series data, you should use techniques like forward is equal to chaining, where you will be model on past data, then look at forward facing data. Fold 1, training 1, test 2. Fold 2, training 1, 2, test 3. Fold 3, training 1, 2, 3, test 4. Fold 4, training 1, 2, 3, 4, test 5. Question number 29. What is a Box-Cox transformation? The dependent variable for a regression analysis might not satisfy one or more assumptions of an ordinary least square regression. The residuals could either curve as the prediction increases or follow the skewed distribution. In such scenario, it is necessary to transform the response variable so that the data meets the required assumptions. A Box-Cox transformation is a statistical technique to transform non-normal dependent variables into a normal shape. If the given data is not normal, then most of the statistical technique assume normality. Applying a Box-Cox transformation means that you can run a broader number of tests. A Box-Cox transformation is a way to transform non-normal dependent variables into a normal shape. Normality is an important assumption for many statistical techniques. If your data is not normal, applying a Box-Cox means that you are able to run a broader number of tests. The Box-Cox transformation is named after statisticians George Box and Sir David Roxby Cox, who collaborated on a 1964 paper and developed the technique. Question number 30. How regularly must an algorithm be updated? You will want to update an algorithm when you want the model to evolve as data streams through infrastructure. The underlying data source is changing. There is a case of non-stationarity, mean variance change over the time. The algorithm underperforms, results lack accuracy. Question number 31. If you are having 4 GB RAM in your machine and you want to train your model on 10 GB dataset, how do you go about this problem? Have you ever faced this kind of problem in your machine learning data science experience so far? First of all, you have to ask which ML model you want to train. For neural networks, batch size with NumPy array will work. Steps 1. Load the whole data in a NumPy array. NumPy array has a property to create a mapping of complete dataset. It does not load complete dataset in the memory. You can pass an index to NumPy array to get required data. Use this data to pass to neural network. Have a small batch size. For SVM, partial fit will work. Steps. Number 1. Divide one big dataset in small size datasets. Number 2. Use a partial fit method of SVM. It requires a subset of complete dataset. Number 3. Repeat step 2 for other subsets. However, you could actually face such an issue in reality, so you could check out the best laptop for machine learning to prevent that.